Okay, let's get started first. Okay, thank you everyone for joining us today. Today it's a great pleasure to have Professor Quanquan Gu from UCLA to give us a talk on his most recent work on large language models. So Professor Gu is an associate professor in UCLA CS department. His research is mostly in artificial intelligence and also, well, more specifically, large language models, reinforcement learning, optimization, span a lot of areas. So he has received a lot of awards, including the Sloan Fellowship, and NSF Career Award, and many others. So without further ado, Professor Gu, it's my great pleasure to have you here today. Thank you, and the floor is all yours.
Thank you. Thank you, Yi, for a very nice introduction, and also thank you. I would like to thank the organizers of this seminar for inviting me. It's my great pleasure to be here, and actually this is my first time visiting UMN. So I really enjoyed my stay here and also the meetings with different people. So in this talk, I'm going to introduce our recent work, which is called self-based fine-tuning, a fine-tuning algorithm for large language models. And if time allows, I will also talk about how to extend this fine-tuning algorithm from large language models to diffusion models for text-to-image generation. So this is a joint work with my PhD student Zixiang, Yihe, Wei Zhuo, and Kai Xuan. Okay, and the first three authors they contribute to this project equal. All right, so with the release of ChatGPT, I think large language models has revolutionized our daily life and work significantly. And I believe many of you, including myself, we benefit from using ChatGPT for editing, for example, emails or making schedules and so on and so forth. But if you look at the past 10 years, the development of deep learning actually has changed a lot. So maybe 10 years ago, when we talk about neural network with, let's say, 23 million parameters was considered as a huge neural network, deep network. But nowadays, the size of the neural network has already increased several orders of magnitude, all the way to, for example, GPT-4, which, although I don't know the exact number, but people believe it may have 1.7 trillion parameters. So you can see that the size of the model has increased a lot. And because of that, it requires more computational power and also it requires more training data. But today I'm not going to talk about how to, for example, study, let's say, optimization or scaling law language model. Instead, I'm gonna talk about how to fine-tune a large language model, which is something I think that people can do in academia because it doesn't require that many computational resources. And I believe many of you here are also study how to fine-tune language or how to do alignment for language models. So generally speaking, there are two kinds of fine-tuning techniques for LLMs. One is called the supervised fine-tuning. So in supervised fine-tuning, you have a high-quality data set curated from humans or some more advanced language model, such as GPT-4. And then you fine-tune the model, maybe a 7 billion model or 30 billion model, using the data from this SFT data set. And the goal of this SFT is trying to enable the models or equip the model with some ability to do some like a downstream tasks, such as reasoning or QA or math problem solving. And the other category of fine-tuning, I call it reinforced learning fine-tuning. People also call it reinforced learning from human feedback. And in this fine-tuning process, inside of have the SFT data set, which is considered as like supervised learning. In our fine-tuning, you have a preference data set. So basically, for each prompt, the model will generate at least 2 responses, and then you ask human or some other language models to tell you which response is more preferred. And based on this binary feedback, the auto fine-tuning will update the model parameter to make the model more and more aligned with the human's preference. Okay, so these are basically 2 categories of fine-tuning techniques people are using in practice. However, both of these 2 fine-tuning techniques face a huge challenge. The challenge is we need a lot of high-quality data set, and many of these data sets actually are generated by humans. So the current research of fine-tuning of language models is trying to reduce the requirement on the number of data or annotations from human, or improve the, for example, the summary complexity or label complexity for LLM fine-tuning. Okay, so in this talk, I will mainly focus on supervised fine-tuning because this is the second step of building a large language model. The first step is pre-training, which is a computationally very demanding. I don't think we can do it in like a university lab, but people in the industry can do it, of course. And the third step is out from human feedback or alignment. I will also skip that step because I think that the second step, supervised fine-tuning, there's already a lot of things worth stuff. So let's take a closer look at the current practice of supervised fine-tuning. They just use the object function from pre-training, and then together use the XFT data set. They just keep pre-train the language models from the pre-training process and update the model parameter to minimize, for example, the cross-entry loss using the XFT data set. And here is an example. So this is an example from data set, the ultra chat 200K data set. So in this example, there's a question. So the question is, in Southampton, what's the most popular form of transportation for commuters? And the ground truth answer to this question is illustrated here. The answer is, I don't have access to the current data. However, historically, the most popular form of transportation in Southampton is buses. The city also has a good network of trains and taxis. So this is also from some humans. And if we look at the response generated from model after supervised fine-tuning, what it looks like. So it says 50% of the commuters in Southampton use cars as their primary mode of transportation, while 20% use public transportation, 12% use bags, and 10% walk. So first of all, the answer is incorrect because the most popular form of transportation is bus, it's not personal cars. Second, it contains a lot of numbers, which looks very accurate. Which looks very accurate, but all these numbers are hallucinated. So this is called the hallucination problems in language models. Okay. So this raises a very natural question. So can we further improve the fine-tuned language model using the XFT data set without using additional data set? So in other words, we think the current XFT step is not fully executed. There's still a lot of information, useful information contained in the XFT data set that can be leveraged to further improve that. And we propose a new approach called a self-paced fine-tuning, which is a more advanced version of supervised fine-tuning. And this fine-tuning algorithm is an iterative algorithm. The high-level idea of this self-paced fine-tuning or spin is we first ask the language model to generate responses given those prompts in the SIP dataset. And then we ask the language model to revert itself to try to differentiate the responses from the human and the responses generated by itself. So as long as the language model can differentiate these two set of responses, which means there's still room to improve for the language model. And until the language model can generate as good responses as humans' responses, then there's no room to improve, which means the fine-tuning algorithm will converge to a good model that can generate equally good responses as like humans. Okay, so this is the high level. And on the right-hand side, you can see that starting from the SIP checkpoint, the model from super fine-tuning, if we apply all fine-tuning algorithm to that checkpoint without using additional dataset, still using the original SIP dataset, the performance of the model can be further improved from like 58% accuracy to 63% accuracy. So more than 5% accuracy. And this improvement actually is like iteration by iteration, because this self-pay fine-tuning algorithm is an iterative algorithm, which I will introduce in detail in the next few slides. And at the beginning of this self-pay fine-tuning, the performance improvement is like more significant. And then improvement will become less and less, and it will become a plateau after 4 iterations. So this is the basic picture of this self-pay fine-tuning algorithm where we apply to fine-tune language models. And you may be curious, after this self-pay fine-tuning, what would the response, model response look like? Okay. So after 1 iteration, we get this response from model. So the answer is I don't have access to the latest updates and the statistics of Southampton. However, there's a like long response I'm not going to read. But the highlight is now the language model does not hallucinate. And second, the language model can tell you that the city also has which include basic trends and variance. Okay. So first of all, it tells you that the most popular transportation for commuters is this public transportation, like basic trains and ferries. And then it also mentions some other like transportations. But at least it doesn't hallucinate those numbers, and it tends to give you like a more accurate answer compared to the answer from the SIP checkpoint. Okay, so there's indeed an improvement after this fine-tuning.
Quick question. So when you compare the two, do you tell the model that you made that hallucination mistake, or simply just
the same prompt?
Just tell it that that's the correct answer?
No, just ask this question.
Yeah. But what do you need to compare with the original SFT data, or?
No. So this response and this response, both of them are responses to the same prompt.
Okay.
Which are basically here. So it doesn't. We didn't tell the model, you hallucinated before. Okay. Yeah. So there's no like COT can solve this kind of adjustment.
Okay.
Yeah.
A couple question.
Yeah.
How is accuracy computed here?
Accuracy. Oh, because we actually. Yeah. So this is the Hugging Face Open LLM benchmark, and it contains 6 different tasks, including, for example, QA, common sense reasoning, math problem solving, and for each task, they have different kind of evaluation. For example, math problem, then for each question, you generate the answer, and they can verify if this answer is correct or not. It's like a binary classification. And for other tasks, they also define the corresponding version metrics. So this average accuracy is average performance over these 6 tasks from this benchmark.
So you said LLM generates its own training data. So for each iteration, since this fine-tuned large language model, so every time you use the new fine-tuned model to generate training data?
Yeah.
Okay. And regarding the quantity of training data, do you have any suggestions? Like,
Oh, yeah, this I will talk about it in
oh,
detail.
okay.
So although the SFT data set contains 200 K data points, we only use 50K. But I think the reason we use that is just for the sake of like computational consideration. But if you use all the, for example, the entire SFT data set, I believe you may get even better result. Yeah. But
the ground truth or the generated synthetic data?
Yeah, so because the problem of self-pay fine-tuning is for each problem, you ask the model to generate a response. And then you compare its response with the response in the SFT data set. You are trying to differentiate these two responses. So basically, if there are, let's say, 200K prompt and response pair in the SFT data set, then during this fine-tuning, you will use 200K prompt along with like 400K responses, because half of them are ground truth responses, half of them are the generated responses.
Okay.
Yeah. So basically, you double the number of training data set, but half of them are synthetic responses from the model itself.
Okay.
Yeah. So I will go to the details shortly, but yeah, that's a very good clarification question. Yeah, I actually mentioned earlier. All right. Now let's go to the technical details of this self-pay fine-tuning. So this is a problem setting. So the input is a sequence X, output or response is another sequence denoted by Y. And the language model can be viewed as a conditional probability P theta. So here theta is a model parameter, and language model basically models this conditional probability of Y given X. And this conditional probability of Y given X can be decomposed as the product of a lot of like conditional probability at each token. So this is called an auto-regressive model because we assume the output conditional on the input actually follows like a markov chain. And this is the like the illustration of self-pay mechanism. So there are two pairs. One is called a main pair, which is LLM at the current iteration. The other is called an opponent pair, which is the LLM from the previous iteration. So you can think of the main pair as the new version of the model, and the opponent pair is the older version of the model. So this game actually is between the new version of the model and the older version, but the same model but slightly different weight. And the main pair is trying to distinguish the opponent's response from the ground truth response. So here, opponent's response means the response from the older version. And the opponent pair aims to generate responses to be indistinguishable from the ground truth responses. And therefore, you can imagine that this self-pay fine-tuning algorithm will consist of two steps within each iteration. The first step is to train the main pair, and the second step is update the opponent. So let me first start with the details of the training of main pair. So here I use I to denote the main pair, and we are going to learn a function f, which is the main pair, to distinguish the LM response and the human response by minimizing this optimization problem. So you can think of this f as like a value function or some kind of alignment score between the input x and the output y. And here there are two different kind of y. One is y that is sampled from p data. So this y is a response from human or from ground truth. The other is y prime. And this y prime actually is the response generated from p theta t, which is a model from the tth iteration. And the larger the value f, the better the alignment between the input and the output. So you can see that if we want to maximize the gap or the difference between fxy and fxy prime, we are trying to maximize the alignment between the input X and the ground truth Y. And at the same time, we want to minimize the alignment score between the input X and the synthetic Y, which is Y. And this X is belong to some function class at T, which I'm going to specify later. So this formulation actually is very related to the integrated integral probability method. For example, if you choose F to be from some like function class of bounded, for example, L1 norm or L2 norm, then this will give you the for example, the T-way distance or what's the distance. And for the sake of optimization, we actually add a loss function L here. Okay. And this L is a monotonically decreasing and convex function. And with this additional loss function, the resulting optimization problem will be more stable. And the next question is how to update the opponent pair. So remember that we need to train the main pair and then update the opponent pair in each iteration. So this is the second step we need to figure out. And the objective of this opponent pair is to find a better language model that can generate responses indistinguishable from the ground truth response. Therefore, this opponent pair, which is denoted by P, okay, is another model, is a new model. And the output from this new model, which is denoted by Y here, we want to maximize the alignment score between X and Y, but at the same time, we want this new model P to stay close to the previous model P theta T. Okay. So P theta T is the model from the Tth iteration, from the previous iteration. So when we are trying to find this opponent pair, which is like a new model, we want this new model to stay close to the older model. Because we don't want the fine tuning to be too aggressive, to move very far away from the original. In that case, the performance may not be good. And at the same time, we want this model, when you use it to generate Y, the alignment score in terms of ft plus 1, evaluated and X and Y, is as large as possible. Because the larger the alignment score, the better. And for this optimizing problem, it has a closed form solution, which is denoted by P height proportional to P theta T times this exponential function. So this P theta T is the previous model, and this exponential function inside the exponential function is lambda inverse times ft plus 1. So this is essentially an exponential weight update to the previous. Now the question is, since the opponent pair has this closed form solution P hat, but we still want this opponent pair to stay within the language model class. So in other words, we want this P hat is still a language model with the same architecture. Right? And in order to achieve this goal, we just assume there exists a parameter theta, or there exists a language model in that language model class, such that P theta equals to P hat. And this is a requirement. And in order to achieve this requirement, we need to choose ft plus 1 equal to lambda, the log likelihood ratio between P theta and P theta. And this result actually suggests that in order to make sure the opponent pair is the language model, but with new parameter, we need to choose this main pair F, which is like alignment score, okay, to be in this form. And this tells you that the function class ft, which I mentioned before, should be chosen as this function class, which is lambda times the log likelihood ratio between P theta, the new model, and the P theta T, the older model. So this is the derivation of the function class for the main pair.
So is there an intuition about this? It looks like a repeating, right?
Yes,
So-
that's a very good intuition here because you can see that the F with the main pair F is in this form. So depending on, for example, if for example P theta is greater than P theta T or P theta is less than P theta T for a certain X and Y pair, the model will be, for example, upweighted or downweighted.
Right. So is it over intuition that as we iterate, we try to emphasize the hard cases?
Yeah,
Right.
yeah, exactly. For example, if X and, for example, actually, I will give you more intuitions later when we derive the convergence result. But the intuition you mentioned, I think, is exactly right. Depending on if X and Y is aligned or not well aligned. If it's not well aligned, then we will add like a larger weight to that. Okay, now this is the two steps within each equation. For the main pair, we just choose it in this form because only if and only if this main pair is in this form, we can ensure that the model after fine tuning in each step is still the same length model class, still belongs to the same length model class. And the opponent pair is just a direct copy of the new model. So this step does not need any optimization. And since this ft plus 1 is in this form, so we can substitute st plus 1 into the previous that object function, which is illustrated here. You can see that previously I derived this form, this automatic form. And then now we know that each f should in this form. Therefore, I just substitute this expression of f into that optimization problem, then get this optimization. And for this optimization problem, the optimization variable is just a theta, the parameter of the new model. So by solving this optimization problem, we just get a new model, which is denoted by P theta T plus 1. Okay. So here's the algorithm. The algorithm is very simple. So it's an iterative algorithm, and T is the index of the iteration. So within each iteration, we first go over the SIP data set, which contains big N number of input-output pairs. And for each prompt xi, we generate the response yi prime using the previous model PCRT. And then we solve this end-to-end optimization problem to get the CRT plus 1. So the intuition is we use the old model to generate the response. And then we compare the response generated by old model and the response by human. We want to differentiate these two. And this optimizing problem is essentially trying to find a new model to differentiate the response from the old model and the response from the human. Okay. And once we have a new model, we will do this synthetic data generation again in the next iteration.
Yeah, I think a related question to the previous one is that, is this related to boosting? Boosting.
Yeah, we thought about boosting in particular, for example, ILBoost algorithm, but I don't see like a very precise connection with
Okay.
boosting. But I think it's indeed related because the update of the model
Exponential updates.
based on exponential.
Right. That's
And,
very similar to boosting.
Yeah,
Yes.
it's related, but I don't know what's the precise connection or relation between this and this.
So from the algorithm, if you could turn to
Sure.
that page,
Yeah.
I fail to understand how lambda is impacting the update on the model.
Okay, great question. So lambda is a regularization parameter, or is a tunable parameter. It's a hyperparameter that we need to tune in our experiment. But where does this lambda come from? This lambda actually is the regularization parameter in this Q regularization. And remember that this Q regularization basically enforce the new model to stay close to the older. So the larger the lambda, and the closer the new model and the old model. So there's a very good intuition to tune this lambda. So if at the beginning, for example, in the first several iterations, you can choose a small lambda, which means you allow the model to train from the old model more aggressive. But in later iteration, you want to use a larger lambda because when the model gets improved, you don't want to update the model too much. You want to update the model very tiny update. In that case, you can choose a larger. And this lambda after derivation, it will appear that's in front of this log application.
Okay.
Thank you for the question. Okay, now let me show some theoretical results. So first of all, as I mentioned,
excuse me, Chen Chen. Sorry, I just muted myself.
oh, okay.
Yeah, may I ask a quick question in the last slide?
Yeah.
Yeah, so my understanding is that here the formulation is based on the main player's perspective. And the way to incorporate the opponent is to use the right score function, which is the log ratio, right? Log density ratio. Is that right? Is my understanding right?
Oh, okay. So I know, yeah. So yeah, probably you better look at this slide. You can see that this log density ratio is the form of the main pair. The opponent pair is just a direct copy of the newly updated model. So that's why even though this is a two-pair game, but we only need to worry about the update of the main pair, because the opponent pair is just the new model, according to this slide.
Okay.
That's why if you look at the algorithm, this algorithm is like a main pair centric.
Okay.
You need the update of the opponent pair, but the opponent pair actually is used to generate this synthetic pair, which is the first, which is the inner for loop. You use the opponent pair to generate the synthetic pair of yi prime, and after that, you don't need to worry about the opponent pair. You just solve this.
Okay, got it. And the L function, the loss function, here, can we just do it as a negative identity?
Yeah, you can do that. But in our instruction, we found that choosing L to be the logistic loss function gives us best result, experimental result.
Okay, so to interpret this loss, I'm thinking to just rewrite the thing within the loss function. So we can actually just do some reorganization so that it becomes lambda log p theta divided by p theta, where the numerator is y, denominator involves y prime, right? And then plus some constant that does not really depend on theta because it only depends on theta t. And so in that sense, if we consider negative identity loss, it's essentially to actually minimize the difference between the log score with in distribution and out distribution.
That's true. But that's probably the reason why the identity loss does not work so well, because if we are choosing identity loss, then when you take gradient with respect to theta, all those terms that depend on p theta t, the gradient equals 0. So theta t will not take any effect during.
Yeah, that's what I was thinking, right? So in that sense, it's not going to be dependent, somehow leveraging the past information, right?
In that case, the past information is only contained in yi prime, which is the data generated from p theta, but it will not appear in the optimizing problem directly. So that's why I think identity loss is not good enough. But if you are using logistic loss or some other loss, where when you take gradient, the gradient still depends on p theta t. In that case, you will have more information to leverage from the older model, from the previous opponent.
Okay. But the choice of the L, do we have any insight, or it has to be somewhat empirically chosen?
In our experiment, we just found the logistic loss.
Okay.
That was the best choice. Yeah.
Okay. Great. Thank you.
Thank you. Yeah, thank you for the very insightful question. So now, just like I said, we can choose different L because the L only need to be monotonic and monotonically decreasing and convex. And you can see that all these three loss functions satisfy these two properties, including the correlation loss, which is similar to the identity loss you mentioned, and the hinge loss and logistic loss. And in our experiment, we found the logistic loss gives the best results. And here's the main thing about the sufficient and necessary condition for the convergence. So under the previous assumption, suppose there exists a P theta equal to P data. So this assumption is called a realizability assumption because we need to assume the language model class is rich enough to contain the ground truth distribution. So under this realizability assumption, we can show that if P theta T equal to P data, then theta T is the global minimum for that optimization problem for any regression factor. But the reverse is not reverse is if P theta T does not equal to P data, then we can always find lambda such that the P theta such that the theta T is not. And given this sufficient and necessary condition, we can show that only if this P theta equal to P data, then we find the global minimum of that. And in particular, because logistic loss is the loss we found to be the most effective in our experiment, so we take a closer look and derive some more results for logistic loss. So if we choose the loss function with logistic loss, under the same assumption as previous theory, we can show that the opponent pair on the new model at the iteration T+1 is proportional to the older model P theta T times this ratio. It's P data divided by P theta T to the power of 1 divided by lambda. So here lambda is the regularization in front of the Shelf regularization. And this suggests that if, for example, P data y given x is greater than this, in other words, if the model, the y and x is not that well aligned, so both of them correspond to incorrect alignment. But this P theta T y given x, if it's less than P beta y given x, which means it should give you a high probability, but it's not high enough, it's lower than the target. Then in this case, this term is greater than 1. So by doing this kind of update, you will increase this conditional probability in the new model. And if this P theta T is greater than P beta, in other words, it's over aligned, then this ratio is less than 1. So by doing this kind of update in the new model, this conditional probability will be pushed down, will be downweighted. So this is the intuition to probably identify or ask previous. And this update here is regulated by lambda, which is the regularization parameter for Shelf regularization. All right, so this is pretty much the theoretical result I would like to share with you. So in the next maybe 10 minutes, let me show some experimental results. So in our experiments, we use checkpoint, which is this 7 billion SIP checkpoint. It's a checkpoint fine-tuned from the Mitra 7 billion model on this ultra 200K data set using standard SIP. And as I mentioned, this data set contains 200K this prompt and response pairs. But in our experiments, we only use 50. But the reason we use VPK is just due to the computational consideration. It's not because using 200K is not good. Okay. And we are using this standard also very widely used Hugging-based open LLM beta board for evaluation, which contains 6 different tasks. And you can see that this is the performance improvement by our fine-tuning algorithm, self-fine-tuning or spin, after 4 iterations. And each column you can see here is a task, and the last one is the average. And you've already seen the performance improvement of average algorithm, which is this. And for each task, you can see that using spin, iteration by iteration, the performance will, in most data set, the performance will increase. But there exists some data set, for example, this renal Grandi or for example, this QA, the performance of this self-fine-tuning may not strictly better than SFT, for example, this or this MMLU. But average, if you take average, then there's a clear performance improvement. And then the second baseline is Zeta GPU, which is a RL phantom model. And you can see that because this RL phantom model uses additional data set, and we don't use additional data set. So without using additional data set, after 4 iterations of the spin tuning, our model is already better than the DPO trap. So in other words, we use less data set, but achieve better performance than RL phantom. So this is another very interesting observation. And the next question is, because our method use half of the synthetic data, remember that we use Y and Y prime. Y is from truth data from the SIP data set, and Y prime is the data generated from previous, so it's a synthetic data. So the next question is, how many SIP data we really need, right? So we just try different size or subset of the SFT data set. And we can see that only use 50K, we can achieve a significant performance improvement. But if you keep running SFT, because you just apply SFT again and again, then even if you are using, for example, 1 epoch of the data set, which is 200K, or 2 epoch of the SFT data set, which is 400K, the performance from SFT can slightly increase, then slightly decrease. So there's no significant improvement if you keep running SFT. But if you run spin, you only use a 50K subset of the SFT data set. You can basically the performance shoot to like 60%. And this is just 1 iteration for spin, and we can run spin 4 iterations to get the performance I show here and also the performance I show at the beginning of the talk. The next question is, because our algorithm is an iterative algorithm, so you need to decide within each iteration, when you solve that optimization problem, how many epoch you want to perform to solve that problem. And this is the everything study. So within each iteration, if we, for example, run 1, 2, 3, 4, 5 epochs, the performance can indeed increase. The overall performance actually is increasing, but after 2 iterations, after 2 epochs, the performance will become plateau, which means inside each iteration, you only need to run 1 epoch or at most 2 epochs. Then you will switch to the next iteration. Switch to the next iteration means you use the new model to generate synthetic data and then do the new iteration. Okay, this will give you better performance improvement because this dashed line is a performance from the next iteration. So in other words, if you don't do this if you don't do synthetic data generation using a new model, you just use the current synthetic data keep running. It's not as effective as you use the new model to generate new synthetic data and then start another iteration. So here's the takeaway. So as I have shown you, this is a theoretically guided fine-tuning algorithm, and empirically works really well. And it can convert a weak language model to strong language model by unleashing the full power of human annotativity. So in other words, this algorithm enables you to mostly leverage the information contained in the SIP data, because it can better utilize the SIP dataset than standard SIP method. And the self-pay mechanism is nice here because no matter the main pair and the opponent pair, both of them are the language model itself. It's different from, for example, generative adversarial network, which contains a discriminator and the generator. But in that setting, the discriminator and the generator are usually chosen to be two different networks. So the training of GAN is changing because you need to deal with two networks. But in our self-pay fine-tuning, this self-pay mechanism, the opponent pair is just a direct copy of the new model. So essentially just a random name pair. And that gives you to do self-pay with its older. So that's a nice thing about the speed. Since I still have maybe 10 more minutes, so I would like to introduce some recent work which generalize this spin algorithm to diffusion models. So diffusion models have been widely used for like data generation, for example, text to image generation or text to video generation. For example, the recently very influential work by OpenAI, the Sora, right? It's a text to video generation. It's also based on diffusion models. And in this talk, I just focused on text to image generation. And there are mainly two major tools. One is called DALL-E, which is invented by OpenAI. The other is called Stable Diffusion, which is invented by Stability AI. And the text generation task is very simple. You just give the model a text prompt, for example, a bird with 8 spider legs. Okay, then the model will generate this picture. All right. Or dragon, duck holding a leg, sound, and so on and so forth. And mathematically speaking, in text to image generation, you have a text prompt denoted by C, and we want to generate an image denoted by X0. And here the X0, this subscript 0 means the true image, because we are using diffusion model, and in diffusion there's a time horizon. So this X0 means t equal to 0. And when we do diffusion, we will just increase the time horizon from 0 to some big t. And we want to learn target diffusion P beta, which is the ideal diffusion that can generate image given the text prompt. And this is the diffusion process, in particular the reverse diffusion process for this unconditional diffusion. The first one, because of the time limit, I'm not going to introduce the detail, but you can see that here X0 is the clean image, and XT to X1 to XT is the noisy image after you inject more and more noise to the clean image. And the generative process, which is a P theta, X0 to T conjunct with the context or text prompt C, can be decomposed in this way. So this is actually a Gaussian process, because the noise we add in this diffusion process is Gaussian noise. And we can show that this Gaussian process actually can be reparameterized by score function, or sometimes we call it a score prediction network, epsilon theta. Okay. And this noising score matching object function can be derived by, for example, minimizing the evidence lower bound, which is so you can think of this epsilon t is the noise you add at the time t, And this epsilon theta of xt context C and T is the predicted noise at time T. And we want to minimize the predicted noise and the true noise. And here the main pair actually is this you can think of it as some kind of function which is also in the form of this log likelihood ratio. I didn't show the detailed derivation, but we can derive something very similar to our previous arithmetic problem, except that in this log likelihood ratio, the likelihood actually is the joint diffusion over x0 to xt, conditional on the prompt C. And this can be further decomposed because this joint conditional probability can be decomposed as a product of a Gaussian conditional Gaussian. So that's why it can be further decomposed into this a lot of like square norm or mean square error minimization. And the one thing I want to mention is because it's a like product of the T conditional probability. So after you calculate this, after you decompose the loss, there's a summation over T. And because this L is a convex function, so by Jensen input, we can move this summation out of the loss function, and which gives you a much clean object function to optimize. And using this spin technique, and based on this optimizing problem we derived, we still do that iterative fine-tuning. So every time we have a new diffusion model, we use this new diffusion model to generate a lot of images for different forms. And then we are trying to differentiate the generated image from the image in some data set. And we use the stable diffusion 1.5 as the base model, and use 4 different performance metrics, include aesthetics, peak score, human preference score, and image reward. So all these 4, except the first one, basically characterizes the appealingness of the image, and the rest 3 scores characterize the alignment between the text prompt and the generated image. So for all the 4 metrics, the higher the better. And you can see that after 3 iterations of this spin fine-tuning, all the performance metrics can be improved significantly and outperform some baseline models, such as the SFT model, which is using SFT to fine-tune the stable diffusion 1.5, or the DPO model, which is RL from human feedback fine-tuning of the stable diffusion 1.5. And we can also show the winning rate of the fine-tuned model. So basically, we just compare the model, the image generated by our fine-tuned model with the image generated by, for example, stable diffusion 1.5. And you can see that the winning rate actually keeps increasing iteration by iteration. And here's one example. So the problem is a snowy Chicago street during Christmas art. And the left image is image generated by stable diffusion 1.5 without any fine-tuning. But you can see that there's no Christmas component in this image. And the image in the middle is the image generated by a model using SFT fine. And you can see there's a Christmas tree show up in the image. And the right image is the image generated by our model. And you can see that not only contains a Christmas tree, but visually more appealing, but it's more warm. And then these are some examples generated by our model using a spin function. So, all right. So in the interest of time, let me quickly wrap up. So in the first part of my talk, I showed you how to use spin to fine-tune any models, and in the second part, although it's very short, so I've already shown you how to use spin to fine-tune diffusion models, in particular the diffusion models for text-to-image generation. So in principle, spin is like a generic approach. It's not specific to language model or diffusion model. You can use you can follow the derivation to derive different version of spin for different kind of models. So so if you believe this spin technique, you can just give it a try, or you can apply it to your own models or to new settings. I think it's a very generic approach. So with that, this is the code and data and models we released. So everything is open source. And with that, I'd like to thank you for listening, and I'm happy to take more questions.
Thank you for a very nice talk. So any other questions from our audience?
Thank you, Chen Chen, for the great talk. Very inspiring. May I ask a quick question regarding the comparison between the SFT and spin?
Yeah, sure.
So my understanding of the formulation level of this SFT is that we try to maximize the P theta y given x. Is that right?
Yes.
So so in our case, from the formula, I'm just trying to think the difference that made the performance difference. Is it because we are contrasting with the generated data from the current model? Is this the primary reason of the performance gain?
Yeah, that's a great question. So so let me answer your question in like two different aspects. The first aspect is for both SFT fine-tuning and the spin fine-tuning, the global optimum should be the same. So both of them should be P data. So P data is the global optimum. I mean, if you consider the population loss, then P data is the global optimum. So in other words, there are different optimization problems for the same global optimum. And this is actually very common. You can conduct the different optimization problems, but the landscape of this different optimization problem could be very different. And some of them can be much easier to optimize than the others. So this is from optimization perspective why spin is better than SFT, even though their optimization problems have the same global optimum. And from the machine learning information perspective, I think your comment is very correct. So because during the spin fine-tuning, we generate a lot of synthetic data, and we use this synthetic data as a reference to tell the model how far the current model is from the ground truth model, the P data. Because you have the data generated from the true model, you have the data generated from the current model. And based on this data, you can tell how far or how different they are, and then you want to minimize this difference.
Okay.
The synthetic data, I think, is mainly used as a guidance to guide the optimization, to guide the fine-tuning process to convert it to the ground truth distribution.
Okay. So if I suppose I have infinite computation power, I generate a lot of possibly infinite synthetic data at every iteration. Would that expect to improve the performance?
So when you say you have infinite computational resources, you want to generate a lot,
Right.
because each synthetic data is the response given the prompt. So unless you have a infinite prompt, otherwise, because for SFT data set is a pair of prompt and response, right? And for this ultra 200K, you only have 200K prompt along with 200K response. So when you do generation, I think you only need to generate the response for this 200K prompts. You don't need to generate the breakdown for each.
Yeah,
prompt.
but for every prompt, if I generated 10 instances of the outcome, would that help? So in your current implementation, is it only one instance per prompt?
Yeah.
Okay.
Yeah, I think it can help, but the performance gain may be very marginal. The reason is, as long as the model can identify or can tell the difference between the ground truth response and the the synthetic response, then there's already good enough or big enough signal to get the model to do the update. So
Okay.
in later iteration, when the model is already very close to the true model or the true data distribution, maybe generate more responses can help. But at the first several iterations, I think that the actual like performance gain brought by this like multiple copies of the response data may not be necessary or may not be significant.
Okay.
That's my guess. I haven't done that experiment,
I
but
see.
I don't
So for SFT, usually how many epochs does it take to train a reasonable result?
for SFT, actually, usually 1 or 2 epochs is good enough because there's a figure I show you in my talk.
Okay.
For example, this one, right? So this blue line, this blue curve is the SFT curve after 1 epoch and after 2 epochs. So you can see that if you keep running SFT by many epochs, the performance improvement is very, very marginal. So there's
Okay.
no point to run SFT for like
Okay.
more than 5 epoch. I don't think that's
Okay. But in terms of the effective sample size, it seems to me that spin also is very small, right? Or because you mentioned only 2, 3 iterations and 1 epoch per iteration. So overall, it's comparable in terms of the effective sample size. Is that right?
Yeah, I think you're right. So the computational wise, I think it's almost the same, except that if you apply spin, you need to do is a synthetic data generation.
Right. So that part is mostly computational intensive, right?
If you have a lot of like GPU, if you do like a parallel generation, actually, it's still less than the cost by solving this automatically. So I think the dominating like computational cost is still from do this automatic part rather than synthetic data generation. But you still need to take into the synthetic data generation into account when you compare time cost of spin and the time cost of SFT.
Okay. And in terms of the decoding algorithm, is that a concern? Is that a matter? Or it's we are just using the same as we use for evaluation?
In our experiment, we just use the same decoding, same decoder, the 3D, and the same as the evaluation.
Okay. Yeah, thanks a lot. Yeah, thanks for the great talk.
Any other comments from the audience? Questions?
Yeah, and my question is the same line because I don't see the deep reason why this is necessary, right? I mean, you talk about the landscape thing. So do you have evidence that it's actually because better landscape?
I don't have evidence or theoretical evidence.
Right, and also, you know, because this is about generalization, right?
Mm-hmm.
It's not only the optimization. So actually the reveating part, let me think about, you know, where the difficulty actually come from. Maybe it's actually because of the non-uniform data distribution, right? It's like your input data, and maybe the joint distribution, you know, they are not uniformly generated from the support. And so some region they are underrepresented. And I suppose, you know, that's where probably the rebating come from.
I'm
Right.
also thinking where the benefit might be that you're emphasizing so at the first iteration, you're treating all the data the same. You do everything, right?
Yeah.
And then at second iteration, you know where you should emphasizing.
Yeah. But right, that's where the rebating come from, right?
Yeah.
But here's the thing. So if your data distribution is generated really uniformly, just imagine that it's uniform with the support, you probably don't need to do that, right? Because there's no sign why some point should be more difficult than others, right?
No, I think that if you take a gradient of this loss function, which I don't show my talk, you can see that for example, the L derivative of this the difference between these two log-like ratio, or you can consider each of them as like pseudo reward. So I think it's still about not about the coverage or if the data is useful somehow or not. I think it's about for some data, the model has already learned better than the others. And in that case, the weight will become
Very
smaller.
similar.
The weight before the gradient will become smaller.
Mm-hmm,
And for those, the other, for example, prompt and response pairs, the model hasn't aligned that prompt and response very well. The weight in front of the gradient will be large. So the model will like spend more effort.
Yeah,
I see,
That's a lot of thinking as well.
So
firstly,
it is
firstly,
very, I mean, the principle is very similar to boosting, right, in that sense.
So you gradually identify
Yes,
which data sets are more harder.
Yes.
Then you sort of set the weights differently.
Yeah.
According to the hardness.
Yeah.
Okay, thank you.
Okay.
One quick question here. So, as you're iterated in your scheme, like 5 iterations, right? So you also use all the same data, SFT data. It's the same, so the prompts are the same.
Actually, in our experiments, we use the current 50K plus the 50K from previous. So basically, we use 100.
Okay, so I was thinking, since you have a lot of others SFT, right? So first iteration you can use the first 50K. Second iteration can use you haven't used.
So the question is,
You could
by the way,
probably
generate.
generate better. Yeah, you could probably generate better.
I think that's true because in the scheme fine tuning for diffusion models, we are using this fresh generated.
Yeah. First
Yeah,
generate.
but in the first paper, we just use a fixed 50K. Yeah, I think there's no particular reason why do it different. Probably just when we started to explore this algorithm at the beginning, we want to be more conservative.
Right.
And later we found, oh, actually it doesn't matter that we just every time we can freshly generate a subset of the XRT data set.
Okay.
Yeah.
Thank you. All right.